Welcome to today's problem walkthrough. We'll be exploring problem number 481, magical string. This is an interesting and slightly unconventional problem that challenges us to think creatively about string generation and counting patterns. Let's dive in and uncover the solution step by step. The problem we are solving involves something called the magical string. This is a string composed solely of the characters 1 and 2, and it follows a specific set of rules. First, no two adjacent substrings containing consecutive characters are identical. For instance, you won't find something like 11 followed by another 11. Second, the string starts with a predefined sequence, 1221121221221221122. From there, the way the string grows depends on its own content. Specifically, the value of the current character determines how many times the next character appears. For example, if the current character is 1, only one occurrence of the opposite character is appended. If it's 2, then 2 occurrences of the opposite character are added. The first character of the string is always 1, and this self-referential process continues as the string expands. Your goal is to calculate how many ones appear in the first n characters of this magical string, where n is an integer input that falls within the range of 1 to 100,000. The output for this problem is an integer that represents the number of ones in the first n characters of the magical string. To clarify the behavior of the string and how this counting works, let's look at an example. Suppose the input n is 6. The first 6 characters of the magical string are 122112. Within this segment, there are exactly 3 occurrences of the character 1. Therefore, the output for this example would be the integer 3. This demonstrates how the magical string is built dynamically while adhering to the rules we discussed earlier, and it shows how we count the ones within a given number of characters. Now, let's take a look at another example. If the input n is 1, the task is to determine how many ones are present in just the first character of the magical string. Since the string always starts with 1, the output here would simply be 1. Next, consider the case where n is 10. The first 10 characters of the magical string are 122, 112, 1221. In this sequence, there are 5 occurrences of the character 1. Again, the output would be the integer 5. These examples help illustrate the process of counting ones in different portions of the magical string based on the input size. To further solidify our understanding, let's focus on the detailed explanation for the case where n is 10. As mentioned, the first 10 characters of the magical string are 122, 112, 1221. Following the rules of the magical string, each character determines how many times the next character appears, ensuring the unique sequence formation. Among these 10 characters, there are exactly 5 occurrences of the character 1. It's also important to consider edge cases as you implement the solution. For example, when n is at its smallest value of 1, the output must correctly return 1. For larger values approaching the upper limit, like n equal to 100,000, the solution must handle efficient string construction and counting to stay within performance constraints. Finally, transitions between groups of 1s and 2s must be managed without errors, ensuring the string grows dynamically without redundant computation. These considerations are key to solving the problem effectively within the given constraints. To tackle the problem of generating the magical string, one approach is to simulate its construction directly using a brute force method. The process starts with the seed string 122 and follows the rules to iteratively generate subsequent characters. Specifically, we read the next number in the sequence, either 1 or 2, to determine how many characters should be appended next. These appended characters alternate between 1 and 2, ensuring that no 2 consecutive groups are the same. While this approach is conceptually simple and provides a clear way to construct the string, it's computationally expensive. As we process each character, the repeated appending and construction of the string result in a time complexity of n squared, which becomes inefficient for large values of n. Additionally, we need extra steps to count the occurrences of ones in the string, adding to the overall computational burden. The space complexity, on the other hand, is n, as we must store the entire generated string in memory. Now, a more efficient approach emerges from recognizing that we don't need to rely on string concatenation to simulate the magical string. Instead, we can use an integer array or list to represent the sequence, which avoids the overhead of continually appending characters. The key insight here is that the magical string alternates between groups of 1s and 2s, with the size of each group determined by the sequence itself. To construct the sequence, we use two pointers. 1, the right pointer, indicates where the next group of characters will be written, while the read pointer reads the current number to decide the size of the next group. This design ensures that the sequence alternates between appending 1 and 2 seamlessly. Additionally, we can count the number of 1s directly during the construction process, eliminating the need for a separate traversal afterward. This approach is highly efficient, with a time complexity of O(n), as each number is processed exactly once, and a space complexity of O(n) to store the sequence. When comparing the brute force and optimized approaches, the trade-offs become evident. The brute force method is easy to implement and understand but struggles with efficiency as n grows larger, due to its O(n²) time complexity. The optimized approach, in contrast, handles even large constraints, such as n up to 10 to the power of 4, with ease, thanks to its linear time complexity. Both approaches require O(n) space to store the sequence, but the optimized strategy eliminates redundant operations, making it faster in practice. From an implementation perspective, the optimized solution does require more careful handling of pointers and alternation rules, but it remains straightforward and achieves significant gains in performance. Ultimately, the optimized approach strikes the right balance between clarity, efficiency, and scalability, making it the ideal choice for solving the problem efficiently. To solve the magical string problem, we start by understanding the sequence and its generation rules. The sequence begins with the seed 122 and grows based on the numbers within itself. Specifically, each number in the sequence determines how many of the next character to append, alternating between 1s and 2s. The task is to generate this sequence and count the number of 1s in the first n elements. To implement this, we initialize the sequence with the seed, represented as a list, magical equals 1, 2, 2. Two pointers are used to manage the sequence. The right pointer tracks where the next numbers will be appended, while the read pointer examines the sequence and determines how many new characters to add. This setup is crucial for efficiently constructing the sequence while adhering to the rules. Once initialized, the sequence is built iteratively. First, we use the read pointer to read the current number in the sequence, which will be either 1 or 2. This number tells us how many times the next character should be appended. The next character alternates between 1 and 2, depending on the last appended value. For instance, if the last added character was a 1, we append 2 next, and vice versa. After determining the character, we append it the required number of times and move the right pointer forward accordingly. This process repeats until the sequence's length meets or exceeds n. Finally, to solve the problem, we count the number of 1s in the first n elements of the sequence using slicing in Python's count method. This approach ensures the sequence is generated efficiently and correctly. Understanding the key insights behind this algorithm is essential. The use of two pointers is particularly important. The read pointer ensures that we process the sequence incrementally, appending only what is dictated by the rules, while the right pointer keeps track of where new numbers are added, preventing unnecessary operations. The sequence alternates between 1s and 2s because of how the rules enforce this alternation, making it straightforward to determine the next character. Additionally, the stopping condition is guaranteed because each rule ensures we append at least one number with every step. For data structures, a list is ideal for storing the sequence since it allows efficient appending and indexing. The two pointers, read pointer and right pointer, are simple yet powerful tools for managing the sequence without revisiting already processed elements. Finally, let's analyze the complexity and account for edge cases. The time complexity of this algorithm is O(n), as each element of the sequence is processed exactly once, either for reading or appending. The space complexity is also O(n), because the sequence is stored in a list that grows linearly with n. For edge cases, if n equals 0, we return 0 since there are no elements to count. When n is less than or equal to 3, the initial seed 122 is sufficient to solve the problem, and we can directly count the 1s. For large n, the algorithm handles the sequence efficiently by avoiding redundant operations, ensuring optimal performance. These considerations make the solution both robust and scalable for varying input sizes. We solve the problem by generating the magical string step by step and counting the number of ones in the first n elements. Here's a detailed explanation of the code. 1. Base cases. If n is 0, the output is 0 because there are no elements. If n is 1, 2, or 3, the seed 122 has exactly 1, so we return 1. 2. Initialization. We start with the magical string s as 1, 2, 2. A pointer head is initialized to 2, which determines how many times to append the next number. The variable number keeps track of the next number to append, alternating between 1 and 2. 3. Generate the string. While the length of s is less than n, we extend s by appending the current number int, s, head, times. Here, s, head, specifies how many times to append the current number. After appending, we toggle number between 1 and 2. We increment head to process the next segment. 4. Count ones. After generating the string, we truncate it to the first n elements and count the occurrences of 1. This approach ensures that we generate only as much of the string as required, making it efficient for large n. The use of a pointer, head, and toggling between numbers keeps the string generation process simple and systematic. The complexity is approximately O(n), as we process each character once. Here, we begin by importing the necessary packages and defining the solution class. The main method of interest is magical string, which takes an integer n as input. The goal is to determine how many ones appear in the first n characters of the magical string. We start by handling edge cases. If n is 0, we return 0 since there are no characters to count. If n is less than or equal to 3, we know the magical string begins with 122, so it contains exactly 1, and we return 1. Next, we initialize the magical string using a list character and populate it with the starting sequence, 1, 2, 2. We also define a pointer head, initially set to 2, which helps determine the length of the next segment, and a number variable, starting as 1, which represents the next number to be appended. The while loop ensures that we build the string until its length reaches or exceeds n. Inside the loop, we calculate how many times the current number should be appended by converting the character at the head pointer to an integer. Using a for loop, we append this number of occurrences to the list. Finally, we toggle the number variable between 1 and 2 and increment the head pointer to move to the next segment. Once the magical string is constructed up to at least n characters, the next step is to count the number of ones in the first n elements. We initialize a variable count ones to 0 and iterate through the first n characters of the list. For each character, if it equals 1, we increment the count ones counter. After completing the loop, the count ones variable holds the total number of ones in the first n characters of the magical string. Finally, we return this value as the result. This implementation efficiently constructs the magical string and counts the required characters, ensuring that the logic is both clear and performant. To solve the problem, we first look at the example where the input n is 6. The goal here is to generate the first 6 characters of the magical string. We begin by initializing the seed string s as 1, 2, 2. This seed serves as the foundation for the sequence. Next, we set head to 2, which corresponds to the index in the string that determines how many of the next number to append. We also initialize number to 1, which represents the number we will add to the sequence. For the first iteration, head points to s2, which is 2. This tells us to append 2 occurrences of the current number, which is 1. As a result, we append 1, 1 to s, updating it to 1, 2, 2, 1, 1. After this, we toggle number to 2, preparing for the next number to add, and increment head to 3. In the second iteration, head points to s3, which is 1. This time, we append 1 occurrence of the current number, which is 2. Adding 2 updates the string to 1, 2, 2, 1, 1, 2. Once again, we toggle number back to 1 and increment head to 4. Now, we check the end condition. The length of the string s has reached 6, which matches the input n. At this point, we stop the loop and determine the output by counting the number of 1s in the first 6 characters of the string. Looking at the sequence 1, 2, 2, 1, 1, 2, we find that it contains 3 occurrences of 1. Therefore, the output for this example is 3. Next, we consider a new example where n is 10. The process begins similarly, with the input specifying that we need the first 10 characters of the magical string. We start with the same seed string s equals 1, 2, 2, and initialize head to 2 and number to 1. For the first iteration, head points to s, 2, which is 2. This means we append 2 occurrences of number equals 1 to the string. After appending 1, 1, the sequence becomes 1, 2, 2, 1, 1. We then toggle number to 2 and increment head to 3. Continuing, in the second iteration, head points to s, 3, which is 1. This indicates that we append 1 occurrence of the current number equals 2. Adding 2 updates the sequence to 1, 2, 2, 1, 1, 2. We toggle number back to 1 and increment head to 4. In the third iteration, head points to s, 4, which is 1, so we append 1 occurrence of number equals 1. Appending 1 extends the sequence to 1, 2, 2, 1, 1, 2, 1. Once again, number is toggled to 2, and head is increment to 5. In the fourth iteration, head points to s, 5, which is 2. This tells us to append 2 occurrences of number equals 2. Adding 2, 2 updates the sequence to 1, 2, 2, 1, 1, 2, 1, 2, 2. After this, number is toggled back to 1, and head is increment to 6. In the fifth iteration, head points to s, 6, which is 1. This means we append 1 occurrence of the current number equals 1. Adding 1 updates the sequence to 1, 2, 2, 1, 1, 2, 1, 2, 2, 1. At this point, the length of the string matches n equals 10, so we stop the loop. To determine the output, we count the number of 1s in the first 10 characters of the sequence. The string 1, 2, 2, 1, 1, 2, 1, 2, 2, 1 contains 5 occurrences of 1. Thus, the output for this example is 5. Finally, we consider the case where the input n is 1. Here, we only need the first character of the magical string. Starting with the seed string s equals 1, 2, 2, we directly take the first n character, which is 1. To determine the output, we count the number of 1s in the sequence. The string 1 contains 1 occurrence of 1. Therefore, the output for this example is 1. This concludes our walkthrough of the solution using these examples. Here, we analyze the time complexity of the solution step by step. First, during initialization, we set up the seed string s equals 1, 2, 2, and initialize variables like head and number. This setup is constant time, or O1. Next, the main string generation happens within a while loop. The loop iterates until the length of the string s reaches n. On each iteration, the value of int s head dictates how many characters, either 1 or 2, are appended to the string. Appending k characters in a list takes k time. As the pointer head moves through the string, it increments by 1 in constant time, and the variable number toggles between 1 and 2, which also takes constant time. Since the string grows approximately linearly with n, the total work done in this step is proportional to the number of characters appended, which gives us an O(n) time complexity for string generation. Finally, after generating the string, the slicing operation to extract the first n elements and the count of ones are performed. Both slicing and counting take O(n) time, meaning this step also has a complexity of O(n). Now, looking at the overall time complexity of the solution, the dominant part is the string generation process, which takes O(n). Since the slicing and counting steps are also O(n), the overall time complexity remains O(n). Next, let's analyze the space complexity. The list s is used to store the generated magical string. In the worst case, its length is approximately n, which requires O(n) space. The pointer head and the variable number are simple variables and only require O(1) space. When slicing the string Sn, a temporary list is created, but it overlaps with the already allocated space for s, so it doesn't add to the overall memory usage. Therefore, the space usage is dominated by the list s, which grows linearly with n. This gives us an overall space complexity of O(n). In terms of best, average, and worst case analysis, the time and space complexities remain O(n). This is because the number of operations depends linearly on n regardless of the input. Comparing this solution to a naive approach, the naive method might simulate the magical string directly by repeatedly determining and appending the next number, which would involve redundant checks and operations. For instance, without using the pointer head, the algorithm would need to recompute segment lengths multiple times, leading to inefficiencies and a higher constant factor in the time complexity. In contrast, the provided solution optimizes the process by leveraging the structure of the magical string. By using the existing string to determine segment lengths, it achieves linear complexity. To mathematically prove the big O, we note that the string grows linearly, appending 1 or 2 characters per segment. Since each operation, whether appending, toggling, or counting, is O(1) per character, the total time complexity is O(n). Similarly, the memory usage is proportional to the size of the string, which is at most n, leading to an O(n) space complexity. When tackling the magical string problem, there are several common pitfalls to avoid. First, not considering edge cases for input size can lead to serious issues. For example, if the input is extremely small, like n equals 1, or very large, your solution might fail due to runtime errors or incorrect outputs. It's critical to test these edge cases to ensure your code behaves as expected. Another common mistake involves inefficient string operations, such as repeatedly appending to strings or using the plus equals operator in a loop. Since string operations are O(n) in many languages, doing this repeatedly can result in an O(n) squared time complexity, which may not scale well. Off by 1 errors and indices are another frequent issue. These occur when you mismanage the current index or pointer, leading to skipped or duplicated characters in the sequence. Finally, overcomplicating the algorithm by introducing advanced data structures or unnecessary techniques can make the solution harder to debug and less efficient. Often, a straightforward simulation is both easier to implement and more effective for this type of problem. Another challenge is handling the alternating patterns incorrectly. This happens when the rules for flipping between 1 and 2 aren't applied properly, resulting in sequences that are either invalid or inconsistent. To avoid this, it's essential to clearly understand the logic driving the sequence generation. Recognizing patterns is key in solving problems like this. Before writing any code, take a moment to validate your understanding of the rules. Additionally, focus on optimizing both memory and runtime. For example, if the problem only asks for the count of a certain character, there's no need to generate the entire string. Instead, aim to produce just what's required. In interview settings, thinking aloud is invaluable. By explaining your thought process, you demonstrate your problem-solving skills even if you don't arrive at the optimal solution right away. Manual simulation can also be a powerful tool. Walking through a few iterations by hand helps you spot patterns and potential bugs. For additional practice, related problems like generate parentheses, decode string, and permutations can help strengthen your skills in generating sequences based on rules. There are multiple approaches to solving the magical string problem, each with its own trade-offs. The brute force approach involves simulating the string generation step by step, appending characters based on the given rules. While this method is simple to implement and easy to understand, it's highly inefficient for large inputs due to significant memory and time consumption. A more optimized approach would be to use a list for string building, as lists allow for more efficient appending. This method also focuses on generating only the portion of the sequence that's needed, making it faster and more memory efficient. However, it requires careful management of indices and pointers to ensure correctness. In some cases, a mathematical insight might reveal a way to compute values directly without generating the sequence at all. This approach is highly efficient in terms of both time and space, but it depends on whether a clear mathematical formula can be derived. If the sequence is too complex for such a formula, this method might not be feasible. Great job making it to the end of this problem walkthrough. We reviewed the magical string and discussed its unique challenges. Remember, simulation problems like this are excellent for honing your algorithmic thinking. If you found this helpful, consider subscribing for more engaging content. Until next time, keep practicing and growing as a problem solver. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!